Hello everyone, and welcome back to Revit Snippets. Great tips you can learn in just a few minutes. Today's lesson is dedicated to showing you how to quickly create this system here of perforation panels entirely in Revit. As you can see, the same system here, I have modeled them as 3D panels in this model here. And unlike other tutorials where they try to create this as a 2D pattern, these are actual 3D panels with actual cutouts, so whenever you try to render them, they will always show their correct 3D geometry. This is looking from the front, and here we have the same panels looking from the back. Now, before we begin, if you are new to this channel, make sure to subscribe now, because we do tutorials like this every single week. Okay, let's get started. To begin, let's create a new Revit file. Just a blank one using any templates you have. It helps if the template has some custom materials you can use later on the panels, but it's not a requirement. Now, let's take a moment and see the reference image one more time. As you can see here, the pattern seems to be guided by a bitmap or an image. You can clearly see that when looking at this side, for example. This pattern in particular is called a Voronoi pattern. If you go to any web browser and just type in Voronoi pattern, that's the style we're looking for. You can see it's very similar as what you can see here and what's showing here in principle for this style. Now we will need to find an image similar to this one, because later on we can take it into Dynamo and tell Dynamo to get a surface, generate lots of holes on it, and then based on a guiding image such as this one, make bigger holes where the image is black and make smaller ones where the image is white. If we go for this one, however, the effect will be a bit different. If we look back into this, it doesn't go quickly from big holes to small holes. There's actually a smooth transition from bigger ones to smaller ones. That means our guiding image shouldn't be all black and white. Instead, it should be based on a gradient of colors from totally black to totally white. Let's see if there's one here. If you cannot find one, don't worry. I have found such an image for you already, and a link to download it will be included in the video description. This is the image. So you can see there, it goes from white to black, but not abruptly. The transition is smooth, and that should help us to achieve an effect very similar to this one in the photo. Okay, let's try to use this one now to generate our perforation panels. To do so, let's go back into Revit, go to Manage, and then open our favorite application, Dynamo. It has opened here, and let's maximize the window for now. We can now create a new definition. By the way, if you are new to Dynamo, don't worry, because I'll go slow and try to explain as much as possible along the way. This will not be a very long and complex script anyway, so you'll be fine. So, step 1, let's bring in that image into Dynamo. I will now right-click and search for File Path. There's a Browse button I can click now. And here, let's select our image. That's the one there. Next step, we can save this Dynamo script before we forget. I'll call this one Perforation number 2. So far so good. We have from here just a file path to this image. Let's turn this path now into an actual file. So I can search for File from Path. And now when I connect this to here, we have converted the path, which is a text, into a file. To see the image in Dynamo, you can also try Image, Read from File. And when we make this connection, you can see the image is there as a bitmap. To see it better, I can also put in here another node called Watch Image. Connect this to there, and there we can see it. That's the same photo from before. Moving on, we will now need a way to convert pixels on this image into values we can use to drive the sizes of our holes in the perforation pattern later on. If you think about it, that information is already there in the image, because each and every pixel in here, they have their own properties, and one of those properties will be the brightness of the pixel. So we have here a two-step process. First, we obtain the pixels from the image, and second, we can then extract the brightness value from the pixels. For the first step, I can now put in here image.pixels. Let's move this one up here, out of the way, and the main flow of our script can continue into this new node. You can see now if I expand the preview window, it says functions. That means this function hasn't been run, and the reason for that is it's missing some input data. In this case particularly, it's looking for how many samples should it get along the x direction, along this line here. The second input data it needs is how many samples should it get along the y direction, which is this line here. If I say use a code block, just double click to place it, and type in here number 5, and then connect it to both input ports. You can see now straight away I have 5 lists, each one containing 5 different colors, because the image has been sampled. So I have here 1, 2, 3, 4, 5 pixels along the x direction, and then another 1, 2, 3, 4, 5 pixels on the y direction. 5 times 5, that's giving me 25 pixels, and that's the same number I have here. From these colors, I can obtain their brightness using another node, which is color.brightness. Connect colors to C, the abbreviation of colors. And when we expand this, we will see 25 different numbers. These are brightness values ranging from 0 for black and 1 for white. When I go down this list here, you can see the range varies from very small number like this one here. That's probably a white pixel, to something a bit bigger. Maybe this one is more gray. So that's the principle. However, we want to have a bit more control over this number of x samples and this one for y. Otherwise, it's going to be a very boring pattern with just 25 holes on it. What we can do here is to put in some real-life measurements. I will double-click here again to place another code block. And now let's see if I can specify the first value for system width. System means the surface that we will try to create panels for. So system width will be, for example, 4000 for 4 meters. Another value we can use is the system height. And that can be also 4 meters for now. So with these two, essentially we have, for example, a wall surface that is 4 by 4, and on that surface we want to generate our perforation panels. For those panels, I need 2 more values. The first one will be hole spacing. The spacing between 2 adjacent holes on the x and the y direction. That value we can try with 300 for now. And the last value we can use will be the spacing between panels' perimeter lines. This is where we can specify how big a panel will be, because for a 4x4 wall, it's unrealistic to have a 4x4 perforation panel, because then it's going to be too big. It's going to be a nightmare to produce and then install it on site. So usually, if we go back to here, that's what they did. For the big surface, they break it down into smaller panels. So this one may be 2 meters on that side and 1 meter high. For our test here, let's go a bit simpler. So for panel size, length, we can use 1 meter for now. So a 4x4 wall divided into 1x1 panels, and on those panels, we should have holes that are 300 millimeters apart. It's good to go now to the next step, which is to find the number of x and y samples. So instead of the number 5 there, which is static, we need to derive from those required dimensions the number of x samples and y samples for this 4x4 wall. To do this, I will put in here another code block. And now we can use a quick formula to find the right values. Let's say I want to have system width divided by hole spacing. The width will be 4 meters, and then hole spacing 300. That gives me 13.3. This will be our value for the number of x samples. So let's connect this to there. We can now do the same for the y direction. So I will just copy this one and then paste it below like this. I can then change the parameter name here to system height and then specify it from this value, also 4 meters. That keeps the same value, of course, but as you imagine, if you vary those two values here, you should get back different numbers of samples on different directions. Okay, that has updated our list of pixels and their color brightness. We have now 65 pixels instead of 25 like before. For the next step, we need to have a proper surface in Revit to generate those panels on. So let's go back in there for a moment. I will now just draw our wall here. That's the simplest way to get a surface in Revit. Let's say this should be 4 meters long. And then go into 3D. I can change this to be 4 meters high. Just like this. Let's hide those levels for a moment. Quite redundant here. And now I want to maybe specify those panels to be laid on this surface. That means I need to bring this surface into Dynamo as a geometry object. Very easy to do so as well. Let's go back to Dynamo here. And then dropped in here a new node called Select Face. With this, I can click on Select and then just select this face here. And you can see face of elements ID, and that's the ID of my wall. That's how we know we have got the face selected properly. Let's now maximize this again and move this face to be starting from there. You can also see it in the preview. If I now click on this and do zoom to fit, that's a wall surface in Dynamo. Moving on, I would like you to forget about those colors and brightness for a moment, and let's focus on creating actual circular holes on this surface. Because without those holes, we have nothing to assign those brightness values to. For these holes, I can create them using another node, and that will be surface.pointAddParameter, this one here. The surface is obviously our surface selected here. Let's click on this and connect there. You can see straight away it has created one point for me already. And that's a point there on the top left corner of the surface. The reason that it's on the top left is because the UNV parameter for this node, their default value is 0 and 0. This is also a good point to explain parameter on the surface for you. In this surface, 0 along the Y direction is here, and 0 for the X direction is also here. X and Y in the context of a surface is called UNV. So if I now change this value from 0 to something else, maybe 0.5, let's say we change that to be the U value. You can see here, U is equivalent to Y, because when I change this value, the point moves up and down. If I instead choose 0.5 to be the V value, it's now going left and right. And that's when we know V in the context of a surface is equivalent to the X direction in the global coordinate system. So far so good, but we need now a lot more points than just one single item there. That means I will need to supply into UNV not one single value like this, but a list of different values. Let's say for example I change this value here from a single one to a number range. The syntax for doing this in Dynamo is this. You can specify the starting number, and then 2 dots, and then the ending number, and then 2 dots, the hash symbol, followed by the number of items you want to have in this number range. Let's say 5 for now, and see what it does. You can see the value is still 1 point, but that's only because lacing is set to be default. If I go here, right click, choose lacing, and go for the longest, I have now 5 points instead of 1. If we now supply the same list of values to the U input, it gives you 5 points diagonally. If I want these points to be a grid, I can now right click here again, choose lacing, and instead of shortest, we can go for cross product. Cross products here only means it will try to match each value here on the U input to each of the values under the V input. So 5 values mapped to 5 other values, that will give you 25 value pairs. And that's how you end up here with 25 points. Very nice. Now, let's take this principle and make it work to our advantage. We need to generate now a list of values, not just from 0 to 1 with only 5 items, but from 0 to 1 with a custom number of items. For example, here I want to have 13 items along the U direction and 13 items along the V direction. An easy way to do that is going back to this code block here and change this static number of items there to a parameter. To do so, you simply have to give it a name. So I will call this one xCount, because that's the number of items or points I want to have along the x-axis. Click away, and now there's an error because there's no value supplied for xCount. Well, guess what? I have it here already. So let's bring this to there. Here we go. Now this will be 13 different values because that's the number I have here from my division. Let's now do the same for the V direction. I will disconnect this for a moment. Maybe give these a bit more space. Bring this down here. Press Ctrl C to copy it and Ctrl V to paste it below. We can now change this name to yCount. Disconnect this now. I can see actually this should be Y, not the other one. So this is Y and this should be X. We can now supply this value to there and the number range to the V input ports. That gives you 169 points because that's 13 times 13. We now have something better to work with. Moving on, I want to make sure before we go any further that the list structure here under the points list should match the list structure under the color brightness list. At the moment they don't match, you can see here this one has 3 levels, 1, 2, 3, and this one below has 4 levels together. An easy way to fix this, and it should work in our case here, is that we can flatten both lists. Let's do flatten here. Bring this to there. And you can have here the same values under one single list. This one there. If I now copy this and use it on the list of points, we now have the same number of points, but under the same list and not nested in any way. A second thing to check is that this list of points and the list of color brightness should have the same number of items. At the moment they not. This is 65 items and this is 169 points. It's happening because here we can have X and Y inputs and they are not matching the U and V inputs under the surface pointed parameter node. This is easy to fix because I can see now this number shouldn't be there anymore. I should replace this with the actual value of xCount. So bring this one here now. Delete this one now. And much better down this way. We now have 169 points. And that perfectly matches the number of brightness values, 169. That means we're good to go. It's now time to create our circles from these points. The node we can use here is circle by plane radius. This one here. For the radius, we'll come back to it in a moment, but the planes, they have to come from these points because these hold the location data that these circles should follow. To convert points to plane, we can use this node here called plane by origin and normal. So imagine you have here a plane, and to create it, you need to define its origin point. That should be the points from this list here, so I'll just go ahead and connect it to there. You can see straight away we have 169 planes already. A second input data that the plane needs is this, the normal vector. You can see in the tooltip there, the default value is a Z vector because 001 is a vector of a length of 1 pointing up. That's not what we want here, and I'll show you why. If I now connect these planes to here, we have already lots of circles coming back. But if I now go to the 3D preview screen and zoom way in, let's see if we can find our circles. It's a bit hard to see, so let's go back to this node interface and gives the circle some radius that is bigger, maybe 100. Now it's clear something's wrong, because our circles, they should be rotated 90 degrees instead. That's easy to do actually. If I go back to the node interface now, we only have to change this normal vector input. And the way to get that value we need is this. Just use surface, normal lat parameter. This one here. The surface we already have, that's the one from before. And the UNV parameter will be identical to what we have here. So I can use the same input there for this, and the same input here for that. That gives me one vector only, because the surface is only one. I had to change lacing again to longest. Still not okay, because only 13 coming back. Let's change this again to cross product. Now that's 169, that's something I can use. However, because those points, they are flattened into a single list, I have to do the same here now. Copy this one down. And make sure our vectors are also on one single list. Now, it's the time for me to connect this, the list of vectors, to this normal input. And straight away, you see, our circles are now rotated and ready for the next step. Now, the time is right for us to vary those circles' radiuses so that I can represent this kind of effect. To do so, we need to get back to this list of values here for color brightness and scale these values to be in the range we need for circle radius. Why I have to do that? This is why. When you look into this list now, that's the list of values from 0 to 1, which is fine on their own. But if I go here and connect this value to the radius input, I can't even see my circles anymore. They are there because I can see them still here, all 169 of them, but the radius of them are just too small. If I go this way, for example, you can see those radiuses. They text those values directly from the list of color brightness, and they're just not big enough to make them visible. To fix this, I need to have a way to scale these values up to a specific range I have in mind for those radiuses. The node to do just that will be math.remap range. So, numbers for the remap command will be those. And here I can specify the new min radius and the new max radius for my circles. Let's use a code block to do this. Let's say the min one can be 5 millimeters and the max radius can be 15. Connect this to there now and get those values that I need. You can see now they are much bigger than the original values because now they have to live between the new min and the new max. It's time now for me to connect those to radius. So something has changed. I can see now there are variations in the sizes of my holes. You can see that one is smaller, that's bigger, and that's even bigger still. So it's working. Okay, it's time for us now to divide the system into smaller panels. You can see here it's not a big system for the whole facade. They have smaller panels there to make it more buildable in a way. To do this, the key thing here is to take out certain circles or holes and put in there lines instead for our panel's perimeters. To do so, I need to go back to the beginning of our script, to here. If you haven't noticed, we have this fourth value that we haven't used any time until now, the panel size length. We can now have a simple formula to derive the number of holes that each panel has to contain. Let's now do another code block for this. And now for speed, let's just say A divided by B. So A, the bigger value, will be the panel size, and B will be the hole spacing, 300. That gives me how much? Just above 3. Don't worry if it's not a whole number. Dynamo will scale and route things up for you where needed. But just for our visualization of the system during development, I can change this value now to 100. And straight away that gives me more points. This value now is 10. That means for each panel in the system, along the X direction there should be about 10 holes. And along the Y direction there should be also about 10 holes. So let's go back to the preview and see what that means. If I look at this corner, for example, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For this column of holes here at index 10, I don't want to have these holes because I want to have instead here maybe a line to denote that's the end of panel 1 on this side and that's the beginning of panel 2 on the other side. That means I need to drop these holes. Let's go back here and do that. The trick is to use another node here called list.dropItem and then use drop every nth item. This one there. The list here will be the list of parameters because we know these parameters they translate directly into holes. So if we omit certain parameters here, these holes will be omitted where needed accordingly. I will now plug these parameters to the list input. For the n, this is the number of items that should pass before one of them is omitted, and then the second pass continue, and then the third pass, the fourth pass, and so on. That number is here already, that's 10. I can now bring this to here now. And the offset is not relevant in our case. Let's see what it produces. I have now 36 items instead of 40 because 4 of them has been dropped from the list. Let's use these and see what it does. I will make another move here, give it more space, and bring this node to here, and then use these values for the U input. Essentially, whenever this node connects to, I want to replace it with this list of results instead. So, following the 2 blue wires, I can see that's 1 and that's 2. 2 places I need to supply these as a replacement. Let's try from here and from there. So straight away, when I go back to the preview, you can see that's 1 row omitted and that's another row of holes omitted. That's the third one as well. The last one also omitted, that's good. Because that's working, let's do the same for the X direction. So I can now Ctrl C, Ctrl V again. Replace this input with this. And then just like before, I can click on this old node and then see that I have 2 places to replace values from this new list of results. So 1 and 2. The preview now looks very nice. I can see now that's holes on panel 1, panel 2, 3, 4 and so on. I have now 16 panels ready to be graded. Anyway, if you look closely, there's something else to fix. When I go to this top corner here, this first row of holes and this first column of holes, they shouldn't be there because that's the boundary of my system. That should just be where my panels terminate. Super easy to fix this as well. Let's go back to the nodes and use another node here called Reconstruct. Essentially, that's just a quick way to say, for this list, separate the first item and give me the rest. So here I can also replace this and that with just the rest of item, excluding the first one. Here we go. Let's give this a bit more space as well. And because it's working for the top row already, I can now copy this and use it to take away the first column of holes. So replace here and replace there. Back to the preview. Now that looks even better. All 16 panels ready to be graded. Now, to make this panel system more complete, we need to also generate the boundaries of our panels. Remember those points that we dropped? We need those points to grade the panel perimeters. So, instead of drop every nth item, I can use a different node, very similar name. This one is list.take every nth item. It's the reverse of this one there. Instead of dropping things, it's gonna get things. So let's go for Y count first. I can now get this list of values to there and also use this number 10 for this n parameter. That gives me 4, which is promising. Let's copy this now and do the same for X count. Again, 4 values coming back. I can now use a second surface dot point at parameter and use these to be the U and the V values. The surface is the one from before, and it's that one there. Let's bring it down here. That's only one value again, so we have to change the slacings here one more time to gross product. And now that gives you 16 points. Next step, I can turn these points, because they are already in groups of 4, into rectangular boundaries. There are different ways to do this, but the most easy way is to use a custom package called Springs. If you haven't got it, just go to Settings, Packages, and do search for the package. In here, just type in Springs. Click on this arrow to install it, and you'll be good to proceed. I've done that already, so under my library I have here this group of nodes under Springs. The one from that package that I want to use is this Quartz by Point Matrix. The points we need obviously are from here, so let's connect this to there. Let's see what's coming out. Didn't change much, but if you look closely, based on the X and the Y values, you can see already those points that have been shifted around, just so that 4 points in the same group actually should belong to the same panel. To proceed then and see the panel, we can use Polycurve by Points, this one. When I connect this to here now, you see lines being created, but they are open because I have also to set this to true. So Boolean, let's try Boolean here with a true value coming into here. Excellent, I can see now I have 9 different polycurves or rectangles in this case. But what's happening for the other panels along the top and the side here? Why were they not created? The reason is this. If I go back to the list of parameters here, you can see we are missing the 0 parameter because that's starting from something else. It's still ending at 1, which is good. That's why we have those panels at this other end of the surface. But 0 has to be in here as well, and also in here. That's easy to do. We can right click and search for list create. Item 1 will be those from here, and then item 0, I can use a code block to just specify the number 0. Get it to here as well, and that's all we need. 0, some values to 1. If I plug this into here, however, it won't do me any good because the list is not flattened. So let's try that now. Bring this one to here, make it a bit more spaces, and use flatten after this list create. That's what I need, so I can plug this straight to here. You can see straight away more panels are now on top. We can now do the same, but this time for the other direction. So Ctrl C, Ctrl V these 3 nodes now. Change item 1 to be those items, and use these for V. Amazing, now we have all 16 panels with their proper boundaries as polycurves. Now, if you don't want to create 3D panels in Revit and you just want to have this pattern maybe in AutoCAD or another program, you can just export them straight here from this point into a file format those other programs can understand. I can show this in another lesson, but for today, our focus is to create proper 3D panels in Revit, so that makes some extra notes in here. Will be surface by patch. This one there. This is to turn those 16 boundary lines into 16 surfaces, as it had done. Next step, I want to also have surfaces for my circular holes. Let's clean up things a bit here so we can see the preview in a better way. I will select everything as I did there, right click and hide all geometry preview. Next step, I can turn on only those surfaces. Maybe those curves can help to visualize things as well. And now we essentially want to cut holes in those surfaces where we have circular objects from there. The node for that purpose will be surface.difference. As you can see in the preview image of this single node here, that's exactly what we need. We have a surface, we have some curves, and we want to cut the surface whenever those curves are. So for the surface, it will be this list here. And for others, when you go to here now, there's a hint next to it. The hint is surface, and that means we cannot use curves for this input. We have to use surfaces. That's also easy to do because we already have their boundaries here as circles. So I just have to put in here a second surface.byPatch node. Connect this to here now, and I have straight away back to me over 1,000 circular surfaces there, very tiny ones. If I want to see their boundaries, I can turn this one preview to be on. And here they are. You can see they vary in sizes. The spacing at the moment between those holes is a bit big. That's why the pattern may not give the same effect you have in the reference image. But as you increase the hole size and decrease their spacing, eventually you will get to this easily as well. Now, before I connect those surfaces to here, I know this node is a bit slow to run because it has to do a lot of geometry manipulation, and especially because here we have over 1,000 surfaces, that will give it a big job to process. So, to make it easier for testing purposes, I will go back here now and change the spacing here to maybe something bigger, maybe 250. That gives you back only a few holes for testing. Once we know it's working, we can always increase the number of holes by decreasing that spacing value. But for now, I can go for this 1 to 1. We still have 16 panels. As you can see, I will save the script and I'll connect this node to there. And now I have back 16 surfaces. It's a bit hard to see how different they are compared to the originals. So let's once again turn off those previews for these 3 nodes. And you can see now, here they are, proper 3D surfaces with holes in them. Anyway, the surface has a value of 0 for thickness, and that's what we want. We want to have proper thickness for those panels. So the next step here is to use surface.thicken. And now I can plug this into there. That will create for me 16 solids from those surfaces. For the thickness, let's go for something realistic, maybe 25 millimeters, and put it to here. When I go back to my preview now in Dynamo, I can see these are now proper 3D geometry, and that's ready for me to render in the Revit model. Or is it? Well, not too fast, because if I go back to Revit now, it's still a blank model with just a single wall. No surfaces has been created from Dynamo in here yet. To make the conversion happen between Dynamo geometry and Revit geometry, I need to use another node here. Now I know there are different ways to bring Dynamo objects into Revit. Some are better than others. But for me, even though some are more speedy and cleaner, sometimes I find that they change the geometry that I have in Dynamo. For example, if I have here a smooth surface with clear boundary lines, if I use another method, when it goes into Revit, that surface may be broken up into a mesh with very ugly triangulation edges on its faces, and that's not what we want. That's why I usually go for this method here, which is to import Dynamo geometry into Revit as an instance, using a reference to the geometry itself. I can now save the script again and turn my solids into import instances in the model. That has done now, as you can see. When I go back to here, that looks pretty great, because here I can isolate one of them. See now, that's actually a 3D panel I can rely on for my rendering or detailing work. Anyway, there's no fun having just 9 holes on each panel. We ultimately want to have this same effect here, so let's tweak a few numbers now to make it happen. I will go back now to the beginning of my script. Before you go crazy with those values, of course it's a good idea to change the run mode from automatic to manual, because now I know it will be a big task for Dynamo to process. I don't want to crash the program when I change this value. So with that set to manual, I can now be safe to maybe change this to a much smaller value, such as 50 mil. So everything's the same wall height, same wall width, same panel size length, but now the hole will be much closer to one another, and that should give me the effect that I'm looking for. With this change, don't forget to save your script, and just click run for the magic to happen. Well, that actually crashed my Revit for some reason. So here I am, just open back up the file and the Dynamo script. I'm quite sure it's not the script that crashed my Revit, something with other programs probably. Anyway, this is where we were before. So just to make sure it's still working, let me just disconnect this node here. I want to see the circles first, to see if they are in the right formation, before we have Dynamo spend time making services and cutting holes through them. So let's run this now. And here they are. Let's have a look. Well, it's actually not very similar to our reference photo, because the pattern here is a bit more regular. It's not as exciting as in the reference project. Let's see what's going on here. We know the number of circles are correct, so their size is a problem, and that could be because of this remap range output. Let's see, maybe I shouldn't have flattened this list here, because sometimes by flattening a list, we might have thrown away valuable information. So let's take this one out, straight to there. Let's see if it helps now. Now we have fewer circles. So this could be because of this blind input. Let's see what we have here. Looks like this flattened node as well could be a problem, because by default it will flatten to the root of the list. So I have here now almost 6,000 points under the same branch. Let's try this. Let's flatten it until there's one level left after the root level. I'll put in here number 1 now and plug it into there. Yeah, that's more like it. So before, we have those in sublists and nested lists. By flattening too much, we actually lost valuable information here. So by flattening to one level left before the whole thing is flattened, we could make it happen. So you can see now, if I zoom out, that's the exact pattern I needed to match the reference project. Okay, things are ready now, finally, for us to reconnect the circle here to make services, and then the rest should work as expected this time. As a good habit, I will save this again, because it may take a while, and then click on run. Oh, speaking too soon. This is actually where we need another flatten node. So let me just put in here, flatten. So before, remember, we were flattening too much. This is where we didn't flatten enough. I need to connect this list now to here, and turn all of those almost 6,000 services into those on the same level. What happens over here is this. We have here services on smaller sublists, and without flattening those first, when I bring those services to here, only services on the first list here, the first sublist, were processed. That's not what we need. We need the whole thing here to come into this node, no omission. So with this in place now, I can connect everything to others, save, and run this again. Alright, here we go. That's looking much better now. We can go back to Revit, and you can see here each panel is fully in 3D. There are individual objects you can hide or unhide. Also, as in the reference project, they have two systems coming together at this corner. We can do the same here as well. Let's go to the top view, select those panels there, and for this I will just do a simple mirror. Maybe against this corner there. And that gives you two faces with perforation panels. Of course, you can repeat the same Dynamo script on this side with another surface, either a wall or something else. But I would only do that if the pattern on this face were different. Otherwise, why not save some time and just copy things around? Of course, if you are very careful with the junction, you can do what I did in the project there and move those panels a bit down like this to avoid any clashing where they join. Also, if you had problems following the tutorial and just want the Dynamo script file, simply go down to the video description and use the link there If you enjoy this lesson and want more like this coming every single week, make sure to subscribe to this channel and turn on the notification bell. That way, you'll be the first to know when I release more lessons. For example, to create this same perforation panel system, but only as a 2D overlay, because obviously doing this for a lot of panels in 3D will take a long time for Dynamo to generate objects and may slow down your Revit model as well. But if you have only a few panels like this, and they are in a very important section of your project where it gets rendered a lot, you can of course do them in 3D this way with Dynamo. For now, practice this new technique, and I'll see you in the next lesson.